Okay, well, that was the kind of standard 3-minute grace period for anybody who, like me, is often late. So I will kick off. Welcome to Transforming Brain Disorder Care with Real-World Data, where we'll be presenting some of the key insights from the multidisciplinary expert system for the assessment and management of complex brain disorders, or MES-CoBraD project. My name is Emily Adrion. I am the director of the Global Health Policy Unit at the University of Edinburgh, and over the last 3 years or so, I've been very fortunate to be part of this consortium. So I'll be moderating today, and I'll be joined by 3 other colleagues who will be speaking to you about some of our key findings. So as we get going, I just wanted to begin with some of the kind of house rules. First, just to make you aware that this session will be recorded, so, don't say or do anything that you wouldn't otherwise want shared publicly. Second, just to ensure that speakers can be seen and heard, we're going to ask that everybody not speaking keeps their camera off and their microphone on mute. And then finally, for any questions that you might have, I think to keep things rolling smoothly because we have limited time, and to avoid any kind of camera or audio related glitches, we'll encourage questions. We definitely want as many questions as you'd like to share, but we'll ask that you share all of those in the chat box. You can share them at any point in the session, but we'll sort of collate them and address them in the Q&A at the very end of the webinar. But feel free to ask throughout, and we have our amazing colleague Oliver Blake, who very kindly has agreed to keep an eye on the chat box for us. So just to give you kind of an overview of what we'll be doing today, I myself will be providing a quick overview of MES-CoBraD so you can get a sense of what it's all about and what we've been doing for 3 years. Then I'll be handing over to 3 of my colleagues who will be presenting results and key findings from the medical perspective, then from a technical perspective, and then finally from an ethical perspective. And we'll end with ample time for discussion and Q&A towards the end of the session. Okay, so with that, I will kick off the session with a really high-level overview of MES-CoBraD, hopefully laying some of the groundwork for you to understand some of the subsequent presentations. So complex brain disorders, or CoBraD as we call them, include neurocognitive conditions, so things like Alzheimer's disease and other forms of dementia, sleep disorders, so things like parasomnia and sleep apnea, and seizure disorders like epilepsy. So these are chronic conditions that are really prevalent, just generally speaking, around the world, but they also exist in combination. And this is really important because these disorders can impact quality of life. They contribute to difficulty in performing what we call activities of daily living and instrumental activities of daily living. So essentially challenges in doing basic things like eating, bathing, and dressing, or managing medications or paying bills. They also increase mortality risk, which is a clear concern. On a health systems level, they lead to financial strain for health systems, but also for patients and their families. So these are a lot of things that we want to focus on, and a reason why complex brain disorders are so critical. So these conditions are, as the name would suggest, complex. They involve multifaceted physiological processes, which contribute to essentially a breakdown of brain rhythms and function. So for that reason, they present a number of key health system challenges. So they require specialist evaluation and treatment. They require integrated care. They require ongoing medical management. And unfortunately, very few health systems are actually equipped to provide the level of specialist services that are required for people who have these conditions. So even in the most well-funded, well-functioning healthcare systems, there are still really important gaps in the care that's provided, and we see a number of patients experiencing underdiagnosis, delayed or misdiagnosis, or receiving suboptimal or contraindicated treatment. So really, access to timely quality healthcare for complex brain disorders is a challenge that we're seeing facing all nations, in part because of this need for really highly specialized knowledge, for multidisciplinary teams, and for personalized treatment and monitoring. And all of these things are really required to make accurate diagnoses and to identify appropriate treatment plans for individual patients. Patients with complex chronic conditions generally, but for example, such as CoBraD, have really unique sets of needs, but there are a range of really important clinical research and technological challenges that are associated with providing treatment for CoBraD. So these include some of the things I just mentioned previously, so underdiagnosis and misdiagnosis, ineffective treatments, but on the research front, they can also include, key gaps that exist in our understanding of the pathophysiology of CoBraD. In terms of technological challenges, we're facing a lack of integrated data platforms and advanced analytic tools to really facilitate treatment. If we think about kind of the clinical and research challenges, complex chronic conditions, generally speaking, are very rarely well addressed through kind of our traditional model of randomized clinical trials. So randomized controlled trials tend to focus on diagnosing and treating single disorders in very controlled settings. They're not good for the messy nature of complex chronic conditions. And we know that complex brain disorders are much messier than this. The real world is far messier than the setting of a randomized controlled trial. So that's really critical, but also crucially, there's a wealth of real-world data, so things like electronic medical records and healthcare claims data, but also things like wearable technologies from smartwatches produce data. And all of these are currently really underutilized in clinical research and clinical care. So the underuse of real-world data and continuous data often leads to really fragmented and incomplete understanding of individual patients' conditions, but also arguably holds back progress in research as well. So addressing these challenges really requires novel boundary crossing efforts. That was the goal of this project. It was a really ambitious project. So MES-CoBraD was funded by the European Commission's Horizon 2020 framework program, and it was really strategically designed to tackle some of these challenges with the goal of enhancing diagnostic accuracy and therapeutic interventions for patients with complex brain disorder. So the goal was to leverage real-world data and take advantage of multidisciplinary expertise, so in medicine, engineering, computer science, but also policy and the social sciences, to really seek to improve quality of life for people with CoBraD, but also their caregivers and wider society. So this is a map showing our consortium partners. So the consortium consists of 14 project partners across 9 countries. We are extremely interdisciplinary, so we have universities, hospitals, we have facilities providing clinical care, we have SMEs, we have software houses, we have 2 partners who focus entirely on ethical and legal issues, we have partners dedicated to dissemination and stakeholder engagement. So, this is a wide consortium of partners across Europe and Israel who are bringing together a number of different disciplines to really do something incredibly ambitious. It's probably worth saying at this stage that the MES-CoBraD platform is far more than just a data repository. That probably would have been very simple, but it's actually designed to be an advanced analytic tool for research, so equipped with a capability for complex hypothesis testing. It also holds the potential to contribute to clinical practice, so offering personalized and targeted diagnostic and treatment plans. And sort of by doing all of this, the goal was to enhance patient outcomes by contributing to, in a really big picture sense, the sustainability of healthcare systems, and to really positively impact the lives of individual patients, but also wider societies within our various nations. So this is just an infographic illustrating what the MES-CoBraD platform offers. It's available on our website. I imagine it's probably a bit small for you to see at the moment. But what the MES-CoBraD platform does is it functions as kind of a cloud-based applied research ecosystem, if you will. And the platform captures kind of the entire research process. So from the collection and anonymization of real-world data to the application of artificial intelligence algorithms, data analytics, visualizations, up to the execution of hypothesis testing and other scientific tools. So we bring all of this together, and the data are securely stored anonymously and accessed through a platform which offers researchers and clinicians a shared repository for their research. So it provides researchers access to multiple data sources in a secure but highly collaborative interdisciplinary environment. So on the right side of the slide, you can see some of the metrics from MES-CoBraD. So we have, well over 600 participants and more than 5,000 real-world data sets that we've integrated into the platform, among others. And I think one of the key takeaways is that the MES-CoBraD platform is really an illustration of what can be achieved when technology and science and medicine all converge to kind of work together to combat complex chronic conditions like complex brain disorders. It's far from straightforward and far from simple, but I think these sort of complex conditions require complex solutions. So hopefully that gave you a quick overview of the project and what we've been doing. Up next, I am going to hand over to 3 wonderful colleagues that I've worked with over the past few years, who will be providing results and key insights from their various perspectives. So we'll begin with Dr. Elissaios Karaveorgiou, who's from the Neurological Institute of Athens, and he'll be providing the medical perspective and insights from the medical perspective. Then we'll hand over to Dr. Christos Ntanos, who will be, he's from National Technical University of Athens, and he'll be providing a more technical perspective and insights from the technical perspective. And then finally, we'll finish with Dr. Francessca Morpurgo, who's from the Cyber Ethics Lab in Italy, and she will be talking about the ethics of AI and taking a more ethical perspective on the project. So with that, I will hand over to Elissaios, who will kick off with some of the medical insights.
Thank you, Emily. Hi from me. I'm a behavioral neurologist and sleep physician here in Greece, coordinating the scientific aspects of the work. Let me share my screen. Here we go. So talking about the results and findings from a medical perspective. So first of all, the idea is that going through pilot use cases that represent both the scientific and social objectives was the way we moved forward. So these aspects have to do with diagnosing patients with CoBraD, making a prognosis, and then also looking at how therapies either affect people and may change prognosis or in a positive or a negative way. In that way, we assigned 4 levels of 4 pilot use cases. The first one was aiming to deeply phenotype complex brain disorders that would allow a comprehensive assessment of them. The second was to use advanced analytic tools, machine learning, and expert system towards phenotyping and prognostication. And then how do we analyze data towards either therapy repurposing or identifying and reassessing approved indications for medication. And then finally, putting it all together into an expert system that can help you in the diagnosis or decisions, therapeutic decisions down the road. So through all our scientific partners put forward hypotheses. So 88 hypotheses were put forward. Since there were too many, we said, okay, let's break them down. So we prioritized, and active leaders were in 50, with several publications and presentations along these years. And first of all, we had a novel protocol that would allow the comprehensive assessment of these disorders. That meant that across at least 5, if not 7 categories of real-world data, patients were assessed across different clinical settings. So either memory clinic, sleep, or epilepsy settings where they were assessed by a physician. They had structured questionnaires and examinations. They had an hour-long neuropsychological testing that was also paper and pencil, but also tablet-based. And then they were followed over a week with actigraphy, with concurrent sleep diary, subjective impressions. And then at the end of the week, or 10 days or so, they had an overnight sleep study with concurrent full EEG. And before and after sleep, we collected blood samples and also performed some sleep-mediated cognitive tests on the reasoning that the dynamics of both cognition and our biofluid markers can also be potentially more sensitive in predicting these disorders and their interrelation. And then for a number of them, there were MRIs. We're talking about real-world data, especially in cognitive and epilepsy disorders. Unfortunately, we didn't have many medical device data or consumer technology data, and these were not prioritized for further analysis. So over the years, you heard before where we have been, how we wrapped up and ranked up to 600 plus participants across institutions through this protocol, both in prospective data that satisfied this protocol. So different institutions had a priori some data that also satisfied these criteria for recruitment, and also and that allowed also for retrospective data to be included towards this end. As a result, we went way above our key performance indicators for almost all of these goals. We almost achieved the full achieving target for a combined polysomnography with EEG. There is definitely more than 100% success for either one or the other across these participants. And we were also very successful in collecting data for underserved populations, and also having almost achieving our aim, where about 17% of participants had longitudinal data to review. So going through the different scientific objectives, first of all, how can we improve early and accurate diagnosis? So deep phenotyping of disorders. So this is work from our colleagues in São Paulo and Barcelona, where episodic memory measures were associated with cortical atrophy. So MRI associations with cognitive performance. And these were seen in people that have Down syndrome. São Paulo is a world-leading center in research on Down syndrome and cognition, and also Alzheimer's disease. And then there is this very interesting new metric where mean cortical diffusivity, and metric of how on a cortical level there is a diffusivity on an MRI metric, can actually be very sensitive in helping in differential diagnosis between the different types of primary progressive aphasias. So neurodegenerative or cognitive disorders that are associated with different neurodegenerative diseases. Carrying on, we had a couple of self-assessment or self-patient or caregiver filled out questionnaires. This work is by Ofer Keret in Rabin Medical Center in Israel, where a new questionnaire that patients and caregivers filled out helped to identify symptoms and their severity towards being able to define whether they had aspects of sleep or mood or cognitive deficit. And all of this was able to help then the clinician towards deciding whether you go forward with a cognitive test or not. So helping towards a screening of patients and directing them in a triage manner. Further work, and this was together with Emily and Ophir, where they looked into, actually Emily's here, but where they looked also at how and whether social determinants of health can affect how long it takes for a patient to be diagnosed. It ended up that there was no statistical significant difference in the time to diagnose according to the area of deprivation index. However, especially certain diseases that are more rare, neurodegenerative disease like posterior cortical atrophy, progressive perinuclear palsy, cortical basal syndrome, they do take longer to diagnose. So that was validated. And that's a bit unexpected from my end, that certain patients, the average patient from the least deprived areas, had longer estimated time to diagnose. And there are some ways to interpret this as far as when they perceive their own first symptoms compared to somebody who comes from a lower socioeconomic area. Furthermore, on the first scientific objective, something that we're interested in here at the Neurological Institute is whether sleep and how sleep is associated with cognitive decline. So we looked at the association between elements of sleep architecture and duration overnight to within day cognitive tests, and we did find certain aspects like how long you stay awake or how long overnight or how long you actually sleep, and this was associated with especially executive function tests. But something very interesting to us was that as some basic or translational research has shown in the past, that sleep-mediated cognitive tests, so what you learned the previous day and being able to remember the next day, was associated both with how long you were awake, but especially with, but also with how deep sleep you got. The most restful sleep is associated with having better cognitive performance the next day. In contrast, we did not find an association with the typical markers that we look for respiratory aspects of sleep. Maybe that will change with larger samples, but it says that if there's a mediating effect, that is likely to be through our sleep architecture. And then moving forward to how can we use further advanced analytic tools for deep phenotyping. And here's again work from São Paulo, where looking into frontotemporal dementia and Alzheimer's disease, they identified markers, biofluid markers, that can track disease severity, especially an astrocytic marker of disease that can be useful in tracking disease severity and cognitive decline over time in FTD, something that was not defined up to this point. Similarly, Down syndrome patients identified the need to screen for AD-related cognitive decline. So how we not just assume that a patient with Down syndrome has other aspects that we just follow and support throughout life, but we actually need to be more specific in assessing cognition as they grow older. Then can we make our assessments faster? So again, work by Rabin Medical Center was that can we look at some simple tests like the MoCA, which is a few minute test that we can do at bedside and a questionnaire of function, compared to an hour-long, more formal questionnaire and exam that is pursued to stage disease. And the answer is that yes, indeed, with an accuracy of around 93%, you can have a very good staging of disease severity in dementia simply by just using these two tests. Then from KCL and in collaboration with also our technical partners, can we look at people that have epilepsy, especially, well, more specifically, that have a focal cortical dysplasia, so changes on the cortex of people that are more likely to end up having epilepsy, and then identify these cortical dysplasias through MRI automated tools. And indeed, using a sample of 85 controls and 85 patients with focal cortical dysplasia, taking 75 of each to train and then 10 of each to test, there was about a 75-77% accuracy in predicting who had and who didn't have cortical dysplasia. Same philosophy also for EEG data. Can we use the EEG data that out of 24 cases in this case who have seizure or periods of seizures and periods without seizures, and can we use and develop a classifier and use it towards saying, okay, there's a seizure period here or there's no seizure during this period, and again high accuracy towards 95%. Going now to scientific objective 3, which was how about treatments? So, okay, we can deeply phenotype, better understand the pathophysiology of disease. We can help in diagnosing and faster diagnosing. But are there ways we can look into treatments that can be effective in people with CoBraD? And this requires really longitudinal data. So we looked at our longitudinal data here at the Neurological Institute, and we had people that had mild cognitive impairment and insomnia. And we randomized people, and that's also in collaboration with a second grant for an intervention by the Alzheimer's Association, where they either received cognitive behavioral therapy for insomnia individually or with a caregiver, or they just received sleep hygiene recommendation. The outcome was that not only did the patients improve their subjective sleep insomnia severity, but also we managed to drop down by a fourth the amount of people, the amount of sedative medications they were taking, whereas the people that in a sleep hygiene group almost doubled or more the amount of medications they were taking. And that's important for us in behavioral neurology because it protects the brain not to be on sedative medication. It can delay cognitive decline. Then coming now to another aspect of how do we put all this in the modern world where we have ethical policy, we have AI and society, all of this trying to figure out how to implement new technologies and advancements. And this is work between Emily and Francessca. They probably will say more later. But the idea is that in practice, you have multiple countries, you have multiple institutions, you have multiple philosophies, and putting it all under one guideline, if you want, will require a lot of policy intervention. That's where probably the European Union is more advanced than the United States. And we're talking from a level of having fair data, having AI regulations, looking into how patient-provider relationships are impacted, how they change, and how the health systems themselves can be ready. And then putting forward structures, processes towards outcomes to achieve that more effectively. Finally, bringing it all together into an expert system, some of the modules that the platform allowed for setting up algorithms, if you want, or using the tools of the system to define algorithms for making a diagnosis. So let's say there are specific criteria. We implemented ourselves a couple for behavioral variant frontotemporal dementia and for sleep apnea. And then based on the data that were fed into the system, you would allow to see if a given patient at a given time satisfies criteria for a given disorder. And that can be integrated in an even larger flow within an expert system towards guiding clinicians of being told that, this guy probably does have that. So that would be the next step for you in either diagnosis or management. So those are some highlights of what we found. Give it back to Emily, I guess.
Thank you. It was really nice to see all of the medical results kind of in perspective, wider perspective, and next to each other. So just as a reminder for anyone who joined a bit late, you're very welcome to share any questions or comments in the chat. You can direct them at specific speakers if you'd like. We'll collate all of these and address them at the end. And now I will hand over to Christos, who will be talking about, I guess, the key insights from the technical perspective.
All right. So, hello, everyone. My name is Christos Ntanos. I'm a research director at the Decision Support Systems Laboratory of the National Technical University of Athens. We will be discussing the technical implementation of the platform's various components, also focusing a little bit on a use case already mentioned by Dr. Karaveorgiou. And we'll show a little bit how the components all join in that unified platform that we've been discussing. So the MES-CoBraD platform attempts to replicate the feedback loop that already exists between medical research and medical practice, but all contained in a software platform. That's a small digital twin for how medicine works. Clinicians collect real-world data from the patients, from their regular visits, and sometimes even from wearable devices, even consumer ones like smartwatches. They then anonymize them and make them available to medical researchers. Medical researchers use these data to train AI models, create new diagnostic and treatment protocols with them, and directly test them by forming scientific hypotheses within the platform. If the results are encouraging and after peer review and approval, they can release the new diagnostic protocols as expert systems, even to the same clinicians that were providing the data in the first place. The reason this can be done is that the data collected, the expert system being trained, its validation and its deployment coexist in the same place, while under the full control of neuroscientists. Engineers provide the technical tools and neuroscientists do the medical work. The expert system is not provided as a proprietary black box by a software company, and to fully address this black box effect of AI, along each step of the processing of the data, the training and the validation of the expert system for each new protocol, metadata is attached, explaining exactly from where the data came, how they were processed, and what AI model was trained using them, along with its parameters. This makes the process fully transparent from start to finish for every loop, and the information is available to the clinician using it. In turn, this would allow them to be in a position to explain it to their patients. We spend a lot of time to design and develop the anonymization of the patient's data, which is done in the Edge module installed in the clinical site. We spent more than a year and a half to get permissions from our clinical sites to start recruiting patients and getting access to retrospective anonymized datasets. Once we start testing the new protocols that use the expert system, we can send them for peer review, as we saw, and then there is the regulatory gap to also be solved. So as a general architecture of the MES-CoBraD platform, which is depicted in this figure, we can observe the interplay of four main elements, each contributing to the overall functionality and security of the system. First, the edge components, which contain also plugins. These are deployed on user machines, which include clinical sites and researcher systems. This is the only part of the platform where sensitive raw data is stored and processed before being anonymized. By processing data locally at the source, the edge components ensure compliance with data protection regulations while preserving data utility for further analysis. This design choice also supports real-time data collection and initial processing, enhancing responsiveness and security. Then, the data integration and harmonization components. This element comprises of the data lake located in a separate environment. Anonymized data from the edge components is transferred there, where it is harmonized and stored securely. The harmonization process ensures data compatibility, facilitating its use in advanced analytics and AI model training. This central repository serves as the backbone of data-driven innovation within the platform. Then we continue with the main platform, which is situated in a different environment to the data lake. This is where the heart of the platform's intelligence resides. It hosts the expert system, advanced data analytics tools, and various machine learning workflows. Here, researchers and clinicians can design, validate, and deploy diagnostic and therapeutic protocols. The co-location of these functionalities within a single controlled environment ensures seamless interaction between medical and technical teams, fostering collaborative innovation. Finally, the security and anonymization framework. This critical layer safeguards the platform's data and operations. The authentication and authorization mechanisms are centralized in the data lake environment, while anonymization occurs locally within the edge components. This distributed approach balances robust security with operational efficiency. The framework ensures that sensitive patient data is accessible only to authorized personnel and remains anonymized throughout the processing lifecycle. Next, we will discuss some of these components in more detail to understand their specific roles and linked challenges. So we will highlight some of the platform's data management architecture, illustrating the life cycle of data as it moves through various stages of processing and integration. First, the data is ingested and depersonalized and pseudo-anonymized. The Edge module deployed locally at each clinical site serves as the primary entry point for real-world data. This modular system is extensible with plugins to depersonalize and deprocess diverse data types, ensuring that sensitive information never leaves the local clinical environment. This guarantees data privacy and secures the initial processing. Then the cloud-based data lake, once depersonalized, the data is transmitted securely to the cloud where it is stored in the platform's data lake. This multi-layer repository acts as the central hub for all data management tasks, accommodating both depersonalized raw data and additional outputs generated by the platform's components. Data harmonization refers to the tool which interacts with the data lake to convert raw data into a standardized format using established healthcare data models such as FHIR. The harmonized data is then stored on the relevant server to ensure interoperability with external healthcare systems. Data sharing and integration refers to the platform's ability to facilitate the interaction between components via the data sharing layer, an SQL query type of engine, and its RESTful APIs. These tools enable efficient data retrieval and manipulation, supporting analytics, visualization, and storage of intermediate results generated by the platform. Now, let's take a closer look at the analytics components of the MES-CoBraD platform. These tools are designed to provide researchers and clinicians with an integrated and flexible environment to analyze complex data related to brain disorders. The process starts with input data, which can come from patient questionnaires, user data, or outputs from medical devices. These data sources are processed and prepared for analysis within the platform, ensuring that they are compatible with the tools we're using. At the heart of the analytics process is the workflow manager. This component allows users to design and organize workflows by arranging tasks, which are modular steps in an analysis process. These tasks can be customized through an easy-to-use interface, ensuring that every workflow is tailored to specific research and clinical needs. The platform features several specialized modules, each tailored to specific types of data. For example, the MRI module processes imaging data for structural and functional brain analysis. The EEG modules handle the EEG signals, performing tasks such as artifact removal and frequency analysis. And the general analytics module supports standard statistical analysis and exploratory data investigation, including hypothesis testing using correlation, ANOVA, classification, clustering, regression, survival analysis, and many more. And finally, the AI module integrates machine learning models for advanced diagnostics and predictions. One of the most powerful features of this system is the support of semi-automated workflows. Once the parameters for a task are set, multiple analyses can be executed simultaneously, significantly reducing the time and effort required from the user. This capability allows researchers and clinicians to focus on interpreting the results rather than managing the process. What's also important to note is that while these tools are integrated into the MES-CoBraD platform, they can also operate independently. Users have the option to manually organize their data and access these tools directly through the platform's interface or APIs, making it a versatile solution for various scenarios. Overall, these analytics components are designed to streamline the research and clinical processes, making complex data analysis more efficient and accessible. By eliminating the need for multiple different tools, the MES-CoBraD platform simplifies workflows and enhances the accuracy and reliability of the results. The MES-CoBraD platform includes powerful MRI analysis tools such as FreeSurfer and FreeView, which allow users to create detailed 3D models of the brain for closer examination. These tools enable cortical reconstruction, which rebuilds the outer layers of the brain in a virtual model, and volumetric segmentation, which divides the brain into different regions for more precise analysis. For brain segmentation, the platform offers two approaches: SynthSeg uses advanced neural networks to automate the process, making it faster and more efficient. On the other hand, SumSeg is a method that does not rely on neural networks, providing an alternative for cases where simplicity or specific requirements are needed. The platform also features dedicated pages for visualizing data. These include easy-to-read tables and interactive brain maps that make the results accessible and understandable. Once the analysis is complete, users can upload the results to the platform, ensuring that they can use them for further analysis or integrate them into workflows. The MES-CoBraD platform includes powerful MRI analysis tools such as FreeSurfer and FreeView, which allow users to create detailed 3D models of the brain for closer examination. These tools enable cortical reconstruction and volumetric segmentation, as we said, and the platform features dedicated pages for visualized data, as you can see here. So if we explore the ability to use AI algorithms for imaging data, we can see a little bit further the example of how we can use the MES-CoBraD platform for this process. It's designed to handle MRI data using advanced deep learning methods. One of its use cases addresses the challenges of distinguishing between MRI volumes. MRI volumes are the three-dimensional representation of the brain generated from multiple two-dimensional MRI scans. We are distinguishing between patients with focal cortical dysplasia, or FCD, and healthy control subjects. Often associated with epilepsy, this requires a precise identification for the accurate diagnosis and effective treatment plan. To achieve this, the MES-CoBraD platform employs 3D convolutional neural network models, as shown in the simple workflow depicted on the slide. These models excel at processing volumetric data, making them highly effective for tasks like analyzing MRI scans. Their implementation is supported by two core functionalities, which is one to train them and one to use them, which we will now see in a little bit more detail. The model training function supports the development of the 3D convolutional models that will be used for analyzing MRI data. The function operates within a training and validation framework to ensure that the models not only learn from the data, but also generalize effectively to new cases. It provides users with significant flexibility to customize the training process according to the specific needs. This flexibility is crucial for tailoring models to the unique requirements of each dataset. When using this function, users can determine elements such as the directory containing the MRI data that will be used for the training, and then the training hyperparameters, including the learning rate, batch size, and the patient's parameter for early stopping. These parameters are essential for optimizing model performance and preventing overfitting. The outputs of this function are designed to provide both immediate feedback and long-term utility. They include visualization plots that display how the loss and accuracy metrics evolve across training epochs. These plots allow users to monitor the training process and identify potential issues such as underfitting or overfitting. A fully trained 3D convolutional model ready for use in inference tasks or future analysis is created and then used. So in the model batch inference function, we allow users to apply an already trained 3D convolutional model to new MRI data and generate predictions efficiently. So to use this function, the user provides two essential inputs: the directory containing the training model, the trained model, which encapsulates the knowledge derived from the previous training that was performed, and the directory of the MRI to be analyzed, ensuring that the system has access to the datasets for inference. Once the process is initiated, the function generates performance evaluation outputs that helps assess the model's predictive accuracy. These include a confusion matrix, a classification, and a classification report. These metrics offer valuable insights into the model's strengths and potential areas of improvement. The function streamlines the application of trained models to other experimental or real-world scenarios, enabling researchers and clinicians to quickly and effectively analyze new MRI datasets while maintaining confidence in the model's performance. Together, these two functions, training and inference, form the basis of how this and other models of AI implementation are implemented in the MES-CoBraD platform. Furthermore, the MES-CoBraD platform supports explainable and trustworthy AI, crucial for building confidence in automated decision-making, especially in medical contexts such as MRI analysis. Let's continue with the example using MRI data. Using FreeSurfer, we can generate statistics in a tabular format with which we can train machine learning algorithms. To ensure these models are interpretable and their decisions are transparent, MES-CoBraD employs explainable AI techniques such as the LIME algorithm. LIME, which stands for Local Interpretable Model Agnostic Explanations, highlights the features most responsible for the model's predictions. For example, in the analysis of MRI data, it can reveal which specific attributes, such as cortical thickness or brain volume, are driving the classification of a patient's condition. To also make a small practical introduction to the next presentation, artificial intelligence in medicine must be subject to rigorous scrutiny, not only because it, like clinicians, is inherently fallible, but also because its use can obscure accountability when errors occur. In other words, how would one know whose fault is it when an AI model makes a mistake that causes a death? This underscores the necessity of legislation and regulation to define clear standards for accuracy while ensuring transparent assignment of responsibility for decisions made by AI systems. In fields such as security, this concept is referred to as non-repudiation, the principle that responsibility cannot be concealed and must be traceable in the event of an adverse outcome. In the context of healthcare, frameworks such as the GDPR, the Medical Devices Regulation, and the EU AI Act, mandating transparency, explainability, and trustworthiness in AI, are designed to work in tandem to address these challenges. Together, they provide mechanisms to ensure that the deployment of advanced AI models is conducted responsibly, with a focus on transparency, ethical considerations, and patient-centered care. These regulations form a vital foundation for integrating complex AI technologies into healthcare in a manner that prioritizes safety and trustworthiness. It is left to the researchers and the implementers of such technologies to develop the appropriate methods to ensure compliance and, in the end, a more accountable, effective application of research in medicine for the real world. Hope this presentation made a few things clear about how the MES-CoBraD platform is built and some of its priorities. I would like to thank you, and I will pass the floor back to Emily.
Thank you so much. It was an excellent overview of platform design and functionality, and I'm really impressed at your ability to make complex functionality really clear and understandable to the rest of us who aren't trained in computer science. So thank you for that. So now I'll hand over to my colleague Francessca, who will be speaking to some of the ethical issues in the project.
Thank you, Emily. Let me share my screen.
We are in the...
Okay, hello to everyone. I'm Francessca Morpurgo from Cybernetics Lab, and as Emily said, I'll be speaking about the ethical perspective, and particularly the ethical framework and ethics of AI model for the MES-CoBraD project. As you heard from the previous presentations, MES-CoBraD is a truly complex project at the intersection of medicine and technology, in particular artificial intelligence. And of course, this is reflected also in the ethical framework of the project, which combines medical ethics and AI ethics. And in this slide, I try to convey this intersection and the fact that, in fact, many themes of the medical ethics and of AI ethics do converge and overlap. For example, Christos spoke about the problem of data and of the protection of patients' data. And of course, this is a problem, a challenge both for medical ethics, respecting patients' privacy and data sharing and reuse, and also for artificial intelligence, where we have also the problem, for example, of the possibility of the anonymization of data, and since we speak of neurodegenerative diseases, for example, of neuroprivacy, because this data could lead really to incredible deep results and insights about people, neurology, and in some sense to their mind. To their minds, but also, I mean, we have also common issues, for example, about the dangers for doctor-patient relationship because, for example, in healthcare, due to limitation of resources, less human resources, less funding, there is the risk also because of the fact that medicine is more and more data intensive, to lose in some way the doctor-patient relationship. And of course, this is a problem also of artificial intelligence when applied to healthcare, the possibility of the humanization of patients and of the personalization of care. So this to say that in the context of this project, we really tried to bridge these two disciplines, two very different disciplines, so medical ethics and AI ethics, and to achieve a common framework that is capable of acting as an ethical guardrail for the project, while also trying to making the knowledge in this field advance. So we try to be of help to the project, but also we try to use the project to find new things and new solutions. So coming to the practical aspects of how the MES-CoBraD ethical framework was implemented and declined in the context of the project, we divided the framework in two. One part about research ethics, of course, focused on patient rights and based on the four principles of bioethics: beneficence, non-maleficence, autonomy, and justice, to which we added the care, the care principle deriving from ethics of care approach, and focusing on human relationships as the pillar of ethical reflection. On the other hand, the part about innovation governance, so a reflection of ethics of technology as applied to healthcare, of course, we adopted as a basis for this part of the ethical framework mainly the trustworthy AI guidelines, and in particular the four pillars of accountability, transparency. Christos, you here spoke a lot about the problem of transparency, trustworthiness, and robustness. And all this conveyed on the definition of an ethical framework that gave to the research, at least we hope so, a solid ethical foundation, and also worked as a basis for pilots assessment. This trying to satisfy one of the societal objectives of the project, so to generate ethical and legal approaches for a trustworthy and sustainable exploitation of the MES-CoBraD platform beyond the end of the project, defining a set of principles for health research making use of AI technology in CoBraD assessment and management. Here you can see the ethical requirement that we derived from the 4 principles of bioethics plus care. So from each principle, we derived a set of sub-requirements, and then we used them to assess and guide the project from the ethical point of view, trying, as I said, to fully integrate bioethics and AI ethics. We did this adopting the principles of bioethics as we are in, healthcare context, as a base layer. And then under the 4 principles of bioethics plus care, we categorized the requirements coming from the Trustworthy AI guidelines and applying, of course, to the technological part of the project. In this way, we continuously monitored and assessed the project during its entire course. We started, as I mentioned, by the definition, with the definition of a set of ethical requirements deriving from the base principles. Then we used this for the first pilot use case assessment, and doing both desk research, so analyzing the work done so far in the context of the project, and also releasing an internal ethical questionnaire. Then we used the findings of this first step and, of course, the general ethical frameworks for defined to identify a set of ethical risks applying possibly to the project, in particular to the AI as it was used and developed during the project. We defined an ethical risk as something that could cause the violation of one or more of the ethical principles that we defined. We performed a risk analysis, and then from these risks, we derived a set of requirements and guidelines that form the basis of the model for ethical AI named ETAI. At last, we used the ETAI for the final pilot use case assessment, during which we also conducted a full risk impact assessment, of course, from the ethical point of view, and we released a second internal ethical questionnaire. So, what is this ETAI model, ethics of AI model? I said before that we didn't want only to act as an ethical guardrail of the project, but we also wanted to try something new. And the problem of not only assessing the ethics of AI and its respect, but also to try to find a way to fully integrate ethics into the development of AI systems is really something that is much researched and talked about. Our ETAI model fosters ethical design principles throughout the developmental stages, trying to ensure that ethical considerations are fully integrated into the structure of artificial intelligence technologies. It starts, the ETAI wants to be something more general than the MES-CoBraD context in which it was first conceived. So we thought about it as an adaptable model and framework that could be modified according to the different contexts and domains. So this is the reason why the first steps are based on a reflection about context, the context of application and the context of organization in which data should be applied. Then also it triggers a participatory reflection about potential ethical issues and problems. And from this, it derives a set of principles, in this case, the principles of bioethics and the trustworthy AI guidelines, that should be considered aside the normative and legal framework, because of course, as Christos mentioned, there are regulations in this field, the GDPR, the AI Act. But as you perfectly know, regulations alone are not sufficient to fully tackle all the questions that may arise in this field that is so open and so much in evolution. Then the next step is to translate principles into values and specific actions and requirements, and then at last there is the attempt of operationalizing this requirement. Coming to the objectives and possible outcomes of the AI, of course, the very first objective is to setting up a tailored ethics standard of AI in healthcare, and to define a framework for the design of AI technologies in healthcare, and of course in CoBraD assessment and management in this case. Then to analyze the reasons that could lead to an ethical misalignment and generate risks or cause negative impacts on patients. And finally, to secure legal and ethical standards, ensuring that the international codes of medical ethics and of practices for artificial intelligence are followed. This could, we hope, so generate many positive outcomes. Of course, for example, guide developers in design and deployment of the system, but also extremely important, reassuring stakeholders that the tool is not going to cause ethical concerns, and this always thinking about possible exploitations of the MES-CoBraD platform beyond the end of the project. The AI has a cyclic and iterative structure. So here you can see a representation of the AI cycle. And the important thing is here that it is not a cascading process where you start with principles, a set of principles, then you define a set of requirements, and at last you deliver an assessment, because I mean, the data model should run ideally during the entire course of the project, and the set of requirements is continuously refined during the various iterations. So only at the very end of the project, a set of recommendations is given and an assessment is performed. We have to say that, I mean, during the MES-CoBraD project, the AI was used mainly as an assessment tool, because there wasn't the time, in fact, to fully integrate it into the development project, even though we worked together with engineers and developers to enter into the design phase. But in any case, here in this other figure, you can see how it was applied into the MES-CoBraD project. And The important thing is that everything starts from the ethics risk identification. After we identified the ethical risks, we evaluated the applicability and likability of the highlighted risks to the project. We categorized the risks under the identified values, so beneficence, non-maleficence, justice, etc. Then we derived ethical considerations from the identified risk, translated them into requirements and assessment criteria, and we used this assessment criteria to perform an assessment of the project and to issue recommendations. Of course, as you can imagine, all this work gave us some answers, but left us and of course all the partners with many open issues. But I mean, this is in some way expectable, as ethics and ethical reflection cannot give definitive answers, but give inputs for further reflection. I think that as we are now at the end of the project, and so we are thinking about what will happen next and the possible exploitation of what we did during the MES-CoBraD project. One of the most interesting open issue is what will happen when a platform like MES-CoBraD will be used at scale, will be integrated into healthcare systems. Of course, as even if we did our best, for example, to ensure transparency, to ensure explainability, to perform a good recruitment of patients, and so have good data sets. As a result, the possibility of biases, also of unknown and hidden biases, is always present. And when the system is used at scale, this could cause, of course, some very negative consequences. For example, cause discriminations, or also wrong diagnosis, even though I mean one can tries to do its best to avoid these negative outcomes. Of course, there are also some issues pertaining to the specific field of application of the MES-CoBraD project that are neurodegenerative diseases. And one of the main risks that we highlighted during the risk impact assessment was the possibility that the project delivers, the system delivers very pristine diagnosis of neurodegenerative diseases, while there is no effective care for these diseases. And so there is a huge ethical problem of what to do with this knowledge, whether it's right to communicate to the patients or not, and what consequences it could have on the life and well-being of involved people. Also, going back to when the system will be used at scale, when you have to take decisions about strategies for entire populations and for entire groups of people. So, of course, these questions cannot have real and proper answers. What it comes out of this work, of this reflection, is that you can try to foresee issues and problems, and to understand what should be the best way of tackling them, respecting the principles and value sets you decided to adopt, and that are conformed with the EU value framework. And here, the role of ethics is something that is quite interesting, because ethics could act as a quickly adapting and potentially fast-changing tool that may provide the first level of protection, even when regulations and laws do not manage to have the same velocity of technology as it evolves really fast.
So we just need to
Christos mentioned
if you
yeah.
can.
Yeah, of course. I finished. Christos mentioned the importance of policies, and all this work should trigger policy reflection, so that these things may be tackled in the most effective and ethical way. Thank you.
Thank you so much, Francessca. And, thank you for sharing your incredible work, which, really bridging the medical and AI ethics formed a really nice backbone for our project, but also, as you said, is innovative and applicable more widely as well, which is a real gift of the project. So now we'll move to an open Q&A. So if you have any questions that you'd like to ask, you're welcome to ask the specific speakers, but we ask that you please use the chat box function to ask the question, just to sort of avoid any audio video delays or glitches as we go. But we'll have all three speakers come back on. While you're coming up with some questions for the speakers, I'll kick off by asking kind of, I guess, maybe a sort of more generic question, which is, I imagine that we have some people in the audience today who are not directly associated with the project, and therefore might be interested in finding out a little bit more about how they might be able to access the platform, or potentially access the data if they're not involved in the project already. So I don't know if Elissaios, you wanted to take this one to start, or others can jump in too.
Yeah, I think that's more of a Christos question on the specifics of the process in getting the data. Otherwise, what we have done up to now, when individual people say, hey, I'm really interested, for example, in the case of the CBTI project, there are bilateral agreements that are signed, but as far as accessing the data on the platform, the approach would be on a platform level. So Christos can answer that.
Yeah, so you can contact the consortium via the project website, which is at MES-CoBraD.eu. At the same time, the platform resides in platform.mes-cobrad.eu. There is a register function there. We don't make research data through the platform immediately available to everyone. We want to make the sharing mechanism be a little bit more controlled at this stage. There is an ultimate aim for the exploitation part of the project and the future versions of it to open up this process into a more streamlined procedure. But by doing so, you can register yourselves as individual researchers, and then contact the consortium to obtain access to data which is shareable within the platform. Now, the concept of how security works in the platform also takes into consideration that individual organizations can have their own space for collaborating, and there's also the ability to create collaborative spaces between different organizations within. So either as an individual researcher or as an organization that wants to bring in a team of collaborators, there are options to register within the platform, and also create those connections with the rest of the consortium to gain access to existing data or upload your own.
Thank you for that. Really helpful. And I guess on this topic, taking it a little bit further and thinking a little bit more about both the presentation that you gave, Christos, and that Francessca gave, I think data security and data privacy are on the forefront of everyone's minds these days. So maybe you can tell the audience a bit more about anonymization and why this is important, and sort of why and how we're dealing with it within the project.
There are two perspectives, two ways to look at it. One is regulatory compliance, and then there is the reasoning behind the regulatory compliance. From a regulatory compliance standpoint, this is GDPR. So based on the mandate by the GDPR, we would have to ask permission by the patients every time that somebody would like to perform research on the data or share the data with other researchers and to perform that. So compliance-wise, the easiest way to avoid that step is to anonymize the data enough as to not be re-identifiable to the initial person, and then the data can live on its own. Now, from a technical perspective, the organization that provides the data will never lose the connection to the original data subject, so the original person providing the data, so the patient from that perspective. So the data subject is supposed to be treated by the institution, by the hospital, so the hospital knows that the data is theirs, but at the same time they want to share that data for research purposes, and also for not only with others, but also within their own team. So what we technologically do in that case is retain the connection within the organization. So the organization in its own systems has the link between the anonymized and the eponymous data, a process which is called pseudo-anonymization, or pseudonymization, as others call it. So they contain that key that links the two. So the people who gain access through the platform, from their perspective, only see anonymous data that don't need special permissions, that cannot be traced back to the individuals or anything like that. And the host institutions that provide the data can use the data to perform analysis on them, use the predictive models and the expert system within the platform to do a diagnosis, run treatment protocols, and all that on it. Last thing about the importance of privacy in this case is that why would somebody care if their medical data is shared? There are cases where people really don't mind if their medical data is shared, because there is a larger perspective, like if they are suffering from a disease and they are desperately seeking help from the research community for new treatments. So in that case, they may even go willingly to share anything about them. That perspective, though, is not shared within the entire population. So the way that things are designed are by default trying to protect the privacy of the patients. And if somebody wants to live outside that amount of privacy, then if they are educated on what that means, they would be able to do so.
Thanks for that. Yeah, I think one of the both interesting and incredibly challenging things about the project is bringing together and balancing sort of the need to have individualized data so that there can be results for individual patients, but also enabling secure anonymization for kind of the wider research community and everything else. So we have a question in the chat from Paulina, who's asking whether our project has anything in common with Data Shield, which is a platform that allows secure access to an analysis of anonymized aggregated health data from various data providers. If you're aware of this platform.
I'm currently on the Data Shield Secure Bioscience Collaboration website. And I do see commonalities, but I think they started after us, so we haven't collaborated or used something from Data Shield. But there are several commonalities.
Probably reinforcing the need to share our learnings and experiences with the wider community as we go. Thanks. So maybe shifting gears a little bit and bringing kind of the ethics and medical perspectives in, you know, I'm curious a little bit about some of the implications that Francessca mentioned in her presentation of AI in healthcare. So she talked a little bit about, you know, concerns around the dehumanization of care because of AI-driven technologies in medicine, and just sort of thinking through how it might impact practice. So I'm wondering if we could have our clinician and our ethicist sort of respond to these issues a little bit. Either Elissaios or Francessca, as you prefer.
Well, I think that Elissaios can provide a much hands-on point of view on this aspect, but from my point of view, of course, if you, have an AI system that is in the middle between the patient and the doctor, depending on how you manage this relationship that is not one-to-one, but there is something in the middle, things may happen. And there is a tendency in current healthcare policies of delegating more and more aspects of healthcare to machines and to AI systems and AI technology. And we are used to think about medicine as profoundly humanistic discipline, no? Where also the history of the patient, the history of the doctor, and the sensations, the experiences are put in and count. So in this sense, there surely is a risk that something is modified, and it may be for the better, but also not. So this is surely an open issue, and yeah, I'm really curious of hearing the Elissaios' perspective about this.
Sorry, because I was trying to multitask as well. If rephrasing it is, how does the current system affect the interaction between physician and patient interaction? Is that accurate? So it has a couple of things. So for the physician and also the use of such platforms and expert system is currently, at least, using it as an aid in your clinical decision making, much as you would refer on your own to a reference book or to a professional association guidelines. But it does it in real time for yourself, or it does it with all the data and validation that goes with it. The explainability that Christos mentioned has a big component behind that, because as a physician, you want to know on what basis this is decided, and that is something that the patient is also aware of. So on the basis of autonomy, from an ethical perspective, the patient makes their own decision, but makes also an informed decision based on the data and how the clinician reached that. And that's something we are expected to do as clinicians either way. I'll try and also combine it with Arieta's question on the chat about informed consent in the context of dementia, specifically in other degenerative diseases, and whether the consent is always valid. So this, and again, has to do also with the work you did with Emily and Francessca, in one of the publications I mentioned. So there are a lot of different legal aspects across countries. In most countries, including Greece, unfortunately, there is a lack of legal prediction of such things. There are general principles that you can follow. There is a law more specifically that is to pass if not in this month, the next month, in Greece on dementia, but it doesn't, in patients with dementia and their legal status, but it doesn't reach the depth or extent of what we need. The general principles in general in this case are that every patient, even if they have dementia, they are still considered competent unless proven otherwise. And or if you have an assumption based on other factors, you can, as a clinician, you can describe capacity, and then the legal system can decide competence. What that means is that capacity is a purely mental state of somebody understanding their state, what options they have, and the outcomes. And this can be, through an expert system, modeled and guide clinicians as they make these decisions. But then the clinician does not have a legal status in making a comment on competence, which is whether they can make legal decisions for themselves. That is purely a judicial system. And that is where the judges, they don't need a clinician to make that decision, actually, but the judges can rely on the decision of a clinician for capacity, or combine it with capacity and make a decision on competence. So the elements of making a decision yourself as a patient, knowing that your clinician, for yourself or for your loved one who has dementia, is based on a framework that is validated, that has assessed their cognitive abilities, their ability for capacity, and within that framework, hopefully one day combine it with what the judicial system says about reaching a decision for competence, allows that merging in an ethical and legal manner. So combining legal and ethical aspects together.
Thanks, Elissaios. I think we probably need to wrap up a little bit.
Yeah, sorry.
I will just add that from a researcher's perspective, there are some really incredibly creative things happening as people work to figure out ways to improve the consent process for people with dementia and sort of reduce capacity. So there are methods like the teach to goal consent process that some researchers are using, but there is an emerging literature on this, which is nice too. Just to add to the, obviously the legal frameworks are the bottom line here. So we unfortunately don't have time for too many more questions. I see Paulina has asked a little bit about the the ETAI model, or how do you say it, ETAI model, Francessca? And
Yeah,
I know Francessca has published on this. We don't really have time for you to answer the question, I'm sorry, because we're already over time. But Francessca has published on this, so there might be a publication that you could pop in the chat, or a link to the publication that you could pop in the chat as we wrap up.
In any case, the super fast answer is yes. It's, I mean, for example, now we are trying to use it for cybersecurity, so it's super customizable and flexible.
Yeah, thank you for that. And as I said, you've done some great work. So there is a publication that potentially you could search for, Paulina, if Francessca doesn't have time to pop the link in the chat. So just to wrap up really quickly, thank you again so much. This was sort of a really quick run through of some of the key highlights and insights that we've had from our project over the past several years. It's been a labor of love, and definitely a labor, but we've had a wonderful consortium full of interdisciplinary colleagues that have worked really hard to pull together the platform that we have. Keep an eye on our website, which will we'll continue to update with some final results and some final kind of project reports, and hopefully provide some indication of future directions. But you can always get in touch with all of us if you have any specific questions on any of these issues. We really appreciate you attending. The event is recorded, so you're welcome to have another view and share it online. But thank you to all of our speakers today, and thank you to Oliver, who's been facilitating this in the background expertly. And we'll wrap up there, but here's to a future of improved care for people with complex brain disorders. Thanks, everybody.